Recently, I saw a video trying to explain that God exists by explaining how complex the Mandelbrot fractal set is. I didn't finish the video because I became enamored when I finally understood actually how the Mandelbrot fractal is calculated. So I decided to implement it in JavaScript, just plain old HTML and JavaScript, and a little smidgen of CSS, and mostly the HTML5 canvas. Let's see. Let's resize everything because everything always gets improperly sized after whatnot. See how big my font size is. Um, it does make it easier on the eyes. So ignoring the HSV to RBG function that I lifted from somewhere else on the internet, I'm using a library here called math.js to handle complex numbers. Basically, let me get Notepad plus plus. Let me see if I can make this a little bigger too. Zoom. Control plus. No. It is Control plus numpad plus. So typically, when you have a polynomial, you have like x minus 3 and x 2x plus 4, and so you expand that like you get the 2x to the squared, and then you get 4x minus 6x, so plus 4x minus 6x is the minus 3 plus minus 3 times 2x is minus 6, and then you get 4 times x, and that's plus 6, and then you have minus 12. So that's a polynomial expansion that leaves you with 2x to the squared minus 2x minus 12. So that's how polynomials work. However, the underlying principle of how fractals work is that they work with complex numbers, and just like x and 3 is a constant and x is a variable, so those terms are kept separate. 2x is a multiplier of x, so that's a coefficient of x, but still kept separate from the 4 because the 4 has no variable, it's just a constant. However, complex numbers are a different beast. So the concept of a complex number is that you have something that cannot be added or multiplied, like a variable, with other numbers, and that is the letter I. I equals the square root of negative 1. Oops, minus 1. So you know that the square root of 1 is 1, but the square root of negative 1 is, well, there's no way to actually, I mean, you can write it mathematically, but there's no way to actually take the square root of that, because you could extract 1 from it and say it's 1i, 1 times the square root of minus 1. However, you're still stuck with the minus 1 in the square root. And since minus 1, square root of minus 1 is 1, this is basically the impossible one. I stands for imaginary, and it means it's frankly impossible to take the square root of. That's the only way to represent this. So they have a constant I. And there's also other, complex constants like j and k. And I don't know how those work. Maybe they're imaginary numbers in other directions. But the idea is that I times I equals minus 1. And that if I had coefficients like 2i plus 3 times I minus 4, let's take that for instance, the polynomial math works out a bit differently. It's like a polynomial in that you multiply the constants and stuff the same way, but both of these figures, the 2i and the 3, are constants basically. The I sort of acts like a variable, but when you multiply it out by itself, it just becomes a whole number. So say I take the first pair, 2i and I, So I multiply 2i to the 2 here, and then I'll take 3i and minus 8i, so plus 3i minus 8i here. Let's just space these out. And then I'll take the last pair, that'd be minus 12. This kind of looks like a polynomial expansion, except that when you take 2i to the squared, it becomes minus 2. And then these figures in the middle become plus 3 minus 8, that's minus 5i. Oops, I'll put that like that, and then that's minus 12. So let's just move that minus 2 and make this a minus 14 here. So the way that math played out is a whole lot different. Let's actually do it for the exact polynomial we had up there. I'll do I minus 3. The original one where x was the polynomial at the top. And we have 2i plus 4. So we'll do this again. So it's 2i squared is minus 2. Minus 6i plus 4i is minus 2i, and then minus 12. So that leaves us with minus 2i minus 14. And how different this looks, because there's no squared terms here. So unlike a polynomial, it does not get more complex. Instead, it remains the same simplicity where there is two parts, a imaginary part and a real part, as a result of this math. So because it behaves different than polynomials, things get interesting when you substitute it as a term in algebra. So a concept of a fractal is that you have z sub, okay, we're going to say z sub j plus, z squared plus c equals z in plus 1 or something. I don't know how to do the little sub here. I'll just do it on the next line. Z in plus 1. There, so, and z0 equals 0. So the way the Mandelbrot fractal works is you're trying to find a value of c. You're testing values of c for which, when you keep adding them into this equation, when you keep evaluating this equation where you plug in the previous version of z into z squared in plus c equals z again, that the value of z converges and stays under 0, or stays small. You know, as the limit approaches infinity, it stays a small number. It does not grow endlessly. Or it does grow endlessly. So how do I explain this? If I chose the value, if I did z squared plus 1 equals z in, so our value of c equals 1. 1 plus 0i. We'll just leave the imaginary component 0 right now, just to illustrate. So you get z squared plus 1 equals z in plus 1. You know, the next value of z. So z starts out at 0, so 0 squared is 0, plus 1 equals 1. So the next value of z, we've got z equals 0, comma, now 1. So we plug in 1 squared plus 1 equals 2. So the next value of z is 2. So now we plug in 2 squared, because we're squaring the last value and then adding it to our value of c. And that's what we're doing literally every single time. So that's 4 plus 1 equals 5. So you can see this sequence is growing. It is clearly showing a pattern of not getting smaller. And it's kind of, I do not want to try to evaluate polynomial math. But you could choose values that are small. For instance, you know that if I did something like chose 0.3, let's try 0.3. So we say as c, so c equals 0.3, z equals 0, and then we have 0 squared plus 0.3 equals 0.3. So then our next term is 0.3 squared plus 0.3 equals ... calculator to the rescue. 0.3 to the 2 is 0.09. So we get 0.39 total. So that's 0.3, 0.39, comma, so then we plug in 0.39 here, squared, plus 0.3. Let's see what we get. 0.39 squared plus 0.3 equals 0.4521. So again, I've chosen a value of c for which it appears that z grows, although it grows slower. Let's choose a smaller value. C equals 2. So z equals 0 for starters. Why did I type x? Trust me, I'm a klutz on the keyboard. I make typos all day long, and I'm a software developer, so I mean, just because you're a software developer doesn't mean you're some sort of superstar. So we'll say 0 plus 0.2 equals 0.2. We'll skip that boring part. 0.2 squared plus 0.2 equals 0.2 to the 2 plus 0.2 is 0.24. I'm afraid this is kind of growing still. So 0.24 squared plus 0.2. I'm not sure if I can get out of this one alive. No. What if I try a negative number? Let's try minus 0.2. Well, that's not working. Minus 0.2. Minus. There we go. Okay, silly calculator doesn't get the fact that I want a 0.2 negative. So I got 0. We're going to try this again. 0 plus minus 0.2 equals minus 0.2. And we're going to take minus 0.2, 0.2, square it, put that in parentheses so you know the minus part is getting squared too, minus 0.2 equals, and that should be 0.2 times 0.2. Wow, this calculator is definitely not liking me. 0.2 times 0.2 equals 0.04. Minus 0.2 equals minus 0.16, I believe. So, our next term is minus 0.16 to the 2 minus 0.2 equals 0.016 times 0.16 equals, so that's 0.0256 there, minus 0.2 equals negative 0.1744. Now let's take this term here and square it, and then minus 0.2 again. We get point, the next one is minus 0.16958 yada. So what you're seeing is at this value, the value does change from iteration to iteration. However, it seems to stay small. So we can say that the coordinate c equals minus 0.2 plus 0I is inside the Mandelbrot set. Now, as I showed you above, once you start doing addition and multiplication with complex numbers, you start to doing a lot of polynomial-ish stuff, except where the x squareds become I squareds and the I squareds just cancel out and become -1. So, wanting to skip that, the Mandelbrot set is calculated by this assertion: what if real numbers are values on the x-axis and imaginary numbers are values on the y-axis? Then what if for each point on the x and y-axis we test a value of c such that I make this notepad bigger so people can actually read it, such that dude, this, all I'm looking for is the font controls. Seriously, Notepad++, make this easier. I have no idea where to find the font. I just want to choose a better, more easily readable font, that's all. Such that for each value of c, where Zn stays small, this is part of the Mandelbrot set. Then you can say, so the way to find out if z stays small is obviously to continue iterating over values of z by continuously plugging this back into itself until you get a sense as to whether numbers get small or whether they get large. Now, I did implement this, and I had a basic version which, let's see if I can just cripple this here. What I did was I chose the max value here and saw if the last value to be returned was less than the max value. But the idea is that when you're checking if each point is in the set, you're running at a fixed number of iterations. You're running this formula a fixed number of iterations, and the detail of the Mandelbrot set that you can get depends on how many iterations of this function you write. You may as well say it helps define the edges of the fractal. But the more iterations you run, the longer it takes to render an image. So you can get approximations at low resolutions by setting like a very low number of iterations, and you'll get a rougher shape. depending on where that border is. And then you've seen those pictures. I'm eating jelly beans. You see those pictures where they got all those wild colors outside the fractal. Well, those colors are calculated by finding out at which point, how many iterations in, that the magnitude of this becomes positive. So if you want to tell if a complex number stays small, you have to basically take the distance of that number. So you know how the Pythagorean theorem works. Let's see here. You got your coordinates. We'll just say it's 4i minus 3. So that might be, say, 3 on the minus 3x, x equals minus 3, and y equals 4. So there's a vector like minus 3 comma 4 here, and you want to find the magnitude of it. Well, you do minus 3 squared plus 4 squared, then you take SQRT of that, and let's put that in parentheses for the mathy computer programmers to know that this is going to be squared altogether. So obviously you know the 3, 4, 5 triangle. This evaluates out to 5 equals SQRT 16 plus 9 equals SQRT 25, just to be thorough, show the work. So in the same way, you can take the magnitude of a complex number by squaring its components. So when you're dealing with a complex number, z also becomes a complex number. And the way to find out if that complex number is staying under a certain amount, like staying under 2, is to figure out the length of that. So you do have to pass it under the Pythagorean theorem. So let's just explain what's happening here. We choose a random complex number. Well, no, we're actually iterating through complex numbers on a grid. And then we're creating a list of points. These are values of z. I am not sure what max len is even for anymore. Kind of looks like I'm not using it. Let me check. Nope, I'm not using it. I'm just going to nuke it. We have I for iterating through iterations. We got z as our initial value, 0, except that now it's a complex number, 0i plus 0. Although the real component comes first, so you may as well say it's 0 plus 0i. I mean, if it's plus 0, it's no different than if it's minus 0, right? I mean, is there some weird, like, plus minus 0, or, like, some sort of strange operand where you're in the strange sneeze, feeling like you got to sneeze between the plus and the minus, you know? Anyway, so z starts out as a complex number equivalent to 0, of magnitude 0. And then we are taking the math, we're taking that complex number, and we are multiplying z. Wait, what am I doing? Oh yes, we are squaring z here just by multiplying the two complex numbers together. So just like polynomial math earlier. And then we're adding c to it. So our number is c. Let's just rename it c. Bang. C bang, C bang. Okay, never mind. So we add c to z here, and then we get the result. And this is basically z n plus 1. So we get the magnitude of that, and we push that magnitude onto the stack. I'm not actually storing individual complex values of z. I am storing the magnitudes of z. But I have result here, which becomes the new z. And then we go back through here, we square it again, add it to c, and repeat. So if So once our magnitude exceeds 2, we are then going to return I, which is the number of iterations it took to exceed 2. And on the other hand, we can return I if it makes it all the way to the last iteration. So let's go. Oh yes, and here is my code for getting the magnitude of the imaginary number. So the complex format in math.js is .re is the real and .im is the imaginary. And this is just a JavaScripty way of saying squared or raised to the power. I don't think it's very often used. Usually people go math.pow, but actually this is slightly fast. So math.pow doing like a bunch of iterations, like did 70,000 or 700,000 iterations, whereas this stars 2 was about a million iterations in the same amount of time. So this one is more performant than math.pow if you're just squaring something. Um, this is just as fast as saying num.re times num.re. So then let's see, convert range. This is just a linear interpolation thing. So while we're iterating through pixels, we can map it to a window of the fractal to render. My canvas is based off of a 2:1 aspect ratio, so it's twice as wide as it is tall. And so the rectangle in which I am picking values of C is within is a 8:4 box where the center is at 0, 0. So x minus 4 is half of width 8, and then y minus 2 is half of height 4. I mean, each time I change one of these values, whatever that is, I render. I'm just using a dark color. I'm not using the light color anymore. Usually the Mandelbrot set is rendered as black, and then everything else is rendered with colors. The HTML5 canvas has probably got to be one of the most confusing things to draw with. But thankfully I was able to use image data and just put image on the canvas and take care of it that way. So what you're seeing here is every time we re-render, I just fill the canvas with a green rectangle, and then I will overwrite image data. I have this little algorithm such that for each time, what was that? Am I actually using pen X and pen Y anymore? No, I'm not. So I think I can just drop it. I was using pen X and pen Y. Let's clean that up. Let's see, let's nuke all this too. I was trying to make an algorithm such that it would skip drawing pixels until the value of until something was in and out of the set. And that's when I was trying to render it in black and white and having a hard time because of this drawing commands, line commands were being really stubborn. So let's just kill that. So anyway, the idea here is I'm batching chunks. I'm not rendering from the center, I'm rendering from the top down. So I'm iterating over y first and doing batches of 5 rows at a time, rendering them, and then for each row I'm iterating through all the x values, so I'm going horizontally. So the idea here is that I have this convert range function that will convert these values here of y. So what happens here is y, as it iterates from 0 to 1,000, gets divided out here by 1,000. Well, actually it'll be divided out by 999 because this will be 0 through 999. This will be subtracted 1 from and divided out from 0 to 0 to 999, so this will normalize into a range of 0 to 1. And then that range of 0 to 1 will be mapped over this frame. And the same thing will happen in the x. So suppose we're at pixel number 500-ish, that will make this value roughly about 0.5 or 1/2. And then what we'll do is we'll say half of the height divided by the height multiplied by that 0.5 would be it's like 4 basically, so we're going to make it 2, and then we're going to add that to the frame rect y value here, and so that would become 0 because -2 plus 2 is 0 basically, so that would put it right in the center of the canvas. Now the reason that these values are negative here is because in HTML y renders from the top down, but in a typical Cartesian coordinate system y actually goes upwards as it goes positive. So I'm just flipping y here. I mean, it's silly. I probably could have just put a minus sign right here and been done with it, but whatever. It is what it is. I will leave it. So then for each pixel of x, we iterate over here, getting a cx value. And then we create a complex number where x is the real and y is the imaginary. And then we check if that point is in the set. Now going up here, you can see this iterations. I don't have a setter for it. Do I? Did I create one? Let me check. Let me check if I created a setter for that. Context menu. Yeah, that was a right click and that's a left click. That's the zoom in feature. But I don't have a setter or a slider or any counter for the iteration. So let's add that in real time here. PID range. I think I print some information about that there. We're going to have span label iterations input type equals number. Min will be 1. Max will be 128. Why not? And then default? No. How about value will equal 1? No, will equal 16ths. No, actually I'm gonna start low so we can see it a little weird. I'm gonna start at 4. How about that? And actually, we're not there yet, but as the iteration values go from low to high, it actually resembles a Fourier transform, like how they do laser light shows and convert the laser movements into there's a really cool series on Fourier transforms I saw. So is this a self? I think inputs are self-closing elements. So I just have to give this guy an ID. I'll call it iterations. And then I will set the label is for iterations here. Now I'm going to go grab that, go over to the JS file here. Oh, let's see. Where are we getting that? So here's where we're getting the canvas. We'll say const iteration control equals document.get element by ID iterations. Now down here we shall say iteration control dot add event listener. Is it change? I think it's change. We'll say it's change. Say event. Cat's a little bored, energetic, probably needs a feather right now. Let's see. we got the change, we got the event. We're going to set iterations equals to, how do I cancel the render? I think I have a way of doing that. Is there a way to cancel the render? Oh, that's right, there is an interval on that. So we'll say clear interval, I think it's just called handle. Yeah, handle. Let's make sure that handle is declared in scope. Yes, handle is in scope. And we'll say handle equals null. And we'll say iterations equal parseInt. We'll say event.target.value. I think it's dot value. Anyway, 10. Make sure to parse it that way. And then, oh yes, for you JavaScripters, calling parseInt with a 10 for the radix when you're working with base 10 is actually faster than calling it without the 10 because it has to kind of guess. So when you give it the radix, you're actually shortcutting its work and making parseInt work faster. Parse float, on the other hand, is a different story. You can't pass a radix into it. Hey, kitty. Okay. Next up here, we got the change, we got the iterations. Well, we're going to call render. So, what this will do, it will allow us to change our value on the fly. The only other thing we gotta do is here iteration control dot value. Let's use a little JS doc because we need to input element to provide it the IDE with the context it needs. Yeah, I'm going to say it's value. So anyway, equals iterations. So we're going to set the default value to iterations there, and then we're going to get our event here. The event target is going to be the thing, so we're going to parse that. So anyway, let us now run it. Where is that? There was a thing for that. Let's look at that parcel. Let's start. Ta-da! This project bootstrapped in WebStorm with Parcel.js. So let us bring that on screen here. Here we have it. Here's a one iteration Mandelbrot set. It's a circle. A circle. That's kind of interesting, actually. Here's a two iteration Mandelbrot set. Kind of looks like two circles, except this one's a little bit more ovally and it's a little feels squished on this side, but that could be an optical illusion. So here's a three iteration Mandelbrot, and it really feels like this is one cycle, this is two cycles, it's ovaloid, and this is kind of three, it's kind of lumpy. It's like a harmonic sort of doodad. Four cycles, it's like 1, 2, 3, 4, 5, 6, 7. It's got, so it's starting to develop peaks and troughs, but you can see the third cycle here surrounding it. And so each of these cycles here, though, represents where the value exceeded 2. The magnitude of the z exceeded 2 after x number of iterations. So as we keep adding to this, we'll keep seeing this number go up. So let's bump it up a bit, shall we? Although I'm not using black as the central fill color, apparently. No, apparently I'm just using... what I'm doing. Let me show you what I'm doing with the color. So the way you get those crazy colors is you map a gradient of sorts to the number of iterations. So let's see, here's update frame. Let's see, scroll up to the render event here. So in our render event, I have an interval that calls this chunk function, and it counts these batches in fives until y reaches 1,000. So this batch is also a multiplier, but it doesn't have to be. It doesn't have to be a multiple of, a divisor, whole divisor or common denominator or whatever you want to call it of 1,000. It could be 6, and that would not divide evenly into 1,000, but it would work. So what I'm doing is I got this do chunk function, and I put in a set interval, and so I call it frequently, and it gives me some sort of responsiveness of the web page while I'm letting it render. So that's good. But how you get the color? So what's going on here is point and set. Sorry, the image data object has 4 values per pixel. One of them I'm completely ignoring here, but let's just basically say that pixel offset is just x values 0 through 2000, then the next row, the next x value 0 through 2000. So going from top down, it's running horizontal rows, then vertically. I'm not sure what I'm saying. So every time we move, we're moving 4 values. But this is each index of this array is an 8-bit digit. This is basically image data is basically a unsigned integer 8 clamped array. And so each image pixel in there is RGB, and then if I had a third one here, so I'm offset plus 3, this would be the alpha. So since we're not really messing with alpha, I'm just editing these values, because alpha is already like 1 or 0 or whatever it needs to be. I think let's see, so opacity has to be 1. I think alpha has to be 0, but don't quote me on that. So if this is included in 0 iterations, I'm setting the color to black. But obviously that's not working. Let's try 1 iteration. We'll try recent included -1 over iterations -1. I don't know, something like that. And so what I'm doing here is I'm using HSV to RGB. So HSV is where the first value is the hue. So you get the primary colors from red to yellow to green to blue to purple and back to kind of red on the other side. So it's like a spectrum. And then this S is the saturation. So it's how rich the color is or how gray it is. And then V is the value, which is is it white or is it color? So actually, if the V was 0, it would be black, and if the V is 1, it would be white, I think. Man, I don't remember how that stuff works, but anyway, so what we're saying is the more iterations it takes, the farther the shift over to purple you get, until you wrap back around kind of at red. And then the saturation, as the iteration count goes up, it fades out towards the edges. So it becomes slightly grayer toward the edges. This is a value from 0 to 1. So basically I'm saying that at 0 iterations, this number is say 16, there are 16 iterations minus 0.5 times 0, so that's 16 over 16 is 1, basically. So you're at a saturation of 1, so you got a rich color. But then as the number of iterations goes up, say the iteration is number 8, so you have iteration minus 0.5 times 8 is 16 minus 0.5 times 8, that's 4. So 16 minus 4 would be 12 over 16 would be 0.75. So this is slightly lower saturation. It's 3/4 saturation. And if I wanted to make the effect more significant, I could just do a straight up subtraction instead of subtracting half. You'd see it really get gray at the edges. And then I'm leaving value at 1. So, okay, so if you have the saturation at 0 and the value at 1, you get white. But if you have the value at like half and the saturation is 0, then you basically get gray. The value was 0, you get black no matter what. So, anyway, I like HSV. It's easier to come up with cool colors than it is in RGB, in my opinion. I don't like working with color in RGB. I really wish they always use HSV, but that's the world for you. Let's see. So we're basically using the number of iterations over the entire number of iterations to calculate what hue to use for things. Then over here, this is supposed to make the center of it black. So maybe now that I've set recent included to 1, we'll see a result. Well, now the middle is white instead. I am perplexed. Let's try switching this to 2. No, instead the black section is here. I'm a little lost with this. Hello, I don't know what I'm doing. Let's see. Ah, there we go. I got the iterations in the wrong order. So the iterations, whenever the number stays under 2, the iterations get higher. So let's try iterations minus 1. Okay, that's still defined. Let's just try iterations, see what happens. So there we go. So I've got this thing backwards. I think that for the saturation, what I'll do is I'll just straight up divide it like this. So I want the colors to be rich in the middle and faded on the outside. There you go. That's more like it. Now I want to do the color in reverse order. So iterations minus recent included. And I'm just going to go iterations -1, or just iterations like this here. Hit save. So we should get red towards the middle now. Aha! There we go. Kind of looks like one of those Indian mandala things or something. I don't know if that's an Indian thing or not, but here we go. So as we bump this up, you'll see more shades because I'm dividing the hue out. But here we go, 27 iterations. Now we're getting closer to what the actual Mandelbrot looks like. Yes, that's a spot on my screen, not in the recording. So as we bump up the number of iterations, this just gets harder to render. But I built into this a well, actually, let's break down this harder to render thing. So the further away from the Mandelbrot set you get, the quicker the magnitude diverges. The quicker our magnitude diverges above 2, which means the sooner that the iterative function renders. So basically, if I were to zoom in here on this portion of the Mandelbrot set here, Mandelbrot, this part renders really quickly because these don't take long to iterate through. I'm on 42 iterations. But as I zoom into the actual Mandelbrot set, the places where it's black are where it's reaching 42 iterations, so it's taking longer to compute. And all the areas around it are also fairly dense in their computational expense. So as I zoom in and you see less and less of the lighter shades here, you're getting to areas that are actually more expensive to iterate. There is a max expense to this, however, and that expense is 42. So each pixel requires 42 iterations at the most, and that would be if you zoomed into the middle of the black portion of the Mandelbrot. Mandelbrot is like, hey bro. Anyway, so all I'm doing here is each time I click in, I'm zooming in by 1.5 and centering the cursor over the mouse, and then recalculating the frame. And so I'm changing the values of X and Y being my top left corner. I have a hidden value for center, and then I have a width and a height. And when I right click, there's a context menu. You know, every web page you right click on, you get this, like this, you get this. This is Edge. Don't hate me, I like Edge. It's actually not that bad. But I especially love this here, this web capture ability where you can just highlight and copy a piece of image on a page to copy paste to someone. It's great for debugging web pages when you're saying, hey, I'm seeing this issue on the web page, just copy it. But when you right click, it actually triggers a context menu event. Let's go to that really quick. I'm going to try and go to it, and it's over here on the other screen. I cheat, I have multiple screens. So I have this context menu event, and you can prevent the context menu from opening by using event.preventDefault inside the handler of context menu. So when I click on the canvas, click event listener, I multiply the zoom by the magnification factor, and here's a zoom. It starts at 1, the center starts at 0, 0, and the maximum size of our window is the initial size up here, is the frame rect. So it's a rectangular region with a height 4 to be a 2 by 1, just like the pixels are 2000 by 1000. Although the truth is even though they're 2000 by 1000, what I'm doing is I'm rendering it as a 1000 by 5000, so I get some kind of anti-aliasing in there for free. I mean, I hope I'm getting anti-aliasing for free. I was reading, now I was told that's what the canvas does whenever, it's stretched or shrunken. So I'm getting a 2x anti-aliasing feature basically, or a 4x if you say it's 2 by 2, but that's what I'm doing to make it look smooth. So magnification factor is 1.5. So each time we click, what we're doing is we're automatically multiplying the zoom by the magnification factor. We're getting the bounding rect of the canvas. Now this is some freaky deaky math, but I'll break it down for you. What we're doing is we're finding out where we clicked relative to the canvas. So if I click, say, let's just pull up the canvas really quick. If I click over here-ish, maybe this is about 200 pixels in from the left side of the canvas. So my client X relative to the page is going to be a different number. So from here, the left side of the page, inwards to about here, this might be like 500 pixels. So here, this value might be 500 for the X. The canvas rect.x is the canvas's left side, which being here from the side of the page might be, say, 300 pixels. So you get my 500 pixels minus 300 pixels is roughly about 200 pixels. And then I'm multiplying that, I'm dividing that by the width of the canvas. So I got 200 pixels divided by the width, which is 1000 pixels, because as I said, the canvas is scaled down, so it's a 1000 by 500 equals about, so 200 over 1000 is about 0.2. It's 0.2. So I'm normalizing my click place on the canvas in a range from 0 to 1 on the X and 0 to 1 on the Y. And then what I'm doing is I'm multiplying that 0.2 by the width of the frame. And then I'm adding that to the negative X offset here. Basically, this, for instance, except it's not the max bounds. It's actually this value up here, the frame rect. So the frame rect changes. But the first point of the matter is that I have to find out where the center is. So the center is wherever I click. So the center I am interpolating as the point at which I click. So I'm calculating relative to the current rendering frame and where we clicked on the canvas, where is our new center. And that's why we're interpolating across the width with this offset, because we're trying to find out where within the frame rect we clicked. So then we got the center X and Y here, and we run update frame. Now let's go to context menu really quick. In this case, I'm just dividing the zoom by the mag factor, so it gets smaller and becomes 1. And if the zoom happens to be less than 1, we set it to 1. So we can never zoom out past 1. And then I'm also taking the center X and Y and deriving it pretty much the same way I did here. In fact, this is repeated logic. The only reason I repeat it is because I'd have to pass the event or the bounding rect into... Yeah, I'd need a client X and client Y and the bounding rect inside of update frame, and I don't want to pass that in. So we recalculate center X and Y here as we zoom out now. And it doesn't matter. The center is wherever you click on the canvas. So we call update frame. Now in update frame, we have a new width and height, which is derived by the bounds, by this max bounds here. So this width of 8 and height of 4 is subdivided by the zoom. So if zoom is 1, you divide 8 by 1, you get 8. 4 by 1, you get 4. But if the zoom is 2, you're looking at a smaller portion of the canvas, so 8 over 2 is 4, 4 over 2 is 2. So your bounds of rendering have gotten smaller. However, your canvas stays the same size. And so that changes up here. Our frame rect y and h and x and w here changes such that cx and cy iterates over a smaller portion of the number the number line. Let's see. So update frame, we get our new width and height. That's the easy math. The complex math is we don't want to allow you to render outside of that 4 by 8 frame. So we're calculating if the center is, minus the new width over 2. So basically the center is halfway between the two extremes of the width. So if the width is 2, for instance, then the center is 1 unit from the right side and the left side of that width. So if the center is like 0.5 and the width is 2, then that width falls outside the border, because 0.5 minus 1 would be minus 0.5, which would mean that we're actually rendering outside the 4 by 8 frame effectively. So we're checking and then correcting the width. We're correcting the center X position to be within those bounds. We're basically shoving it back in bounds. And I'll give you a little example of this here. I'm going to zoom back out. So we're at width and the height 8 and 4. And don't ask me how I guessed that this was the perfect bounds to encapsulate the Mandelbrot set, but I just kind of guessed that it would have a small variation. Apparently it would fit easily in width 4, height 4. So if I click here, as you see, this top circle is staying within the bounds. You can see that even though I go up here, the edge of the circle, if I clicked here and it was going to go to the middle, the edge of the circle would be right here, but it's at the top. So I am basically, with my math, forcing the view to stay in bounds. And I'm forcing you to zoom out back to the max bounds. So this is centering the X, centering the Y. And then this here is basically how we get the new X and Y. Basically, if the center is at the 0, 0 of the window, the very middle of the window, then basically the new X is the center minus half of the width. So if the center is at 0 and the width is 8, then our X should be minus 4, which is what we have here, minus 4 and 8. So we actually have to measure everything by the top left corner, vaguely speaking, instead of the center. So that's why we're recalculating in terms of the top left corner or the bottom left corner. And but the center helps us figure out where we're zooming in on. So it's handy. And then, W and H is obvious. And then we're just setting these numbers here so that you can see them here. That's all that's doing. Then once we've set that update frame, we just call render, and it starts rendering again with the new values. But honestly, I should probably do that because a good clear interval would help. It would help. Stop rendering so that we can update then re-render. Otherwise you'll just kind of see what you would call screen tearing in a video game, except this is at almost 0 frames per second, So there you have it. Bit of Mandelbrot. So I corrected so many bugs just talking about this with you. So let's jack up, while we're looking at it at this size, let's jack up and see the number of iterations. You can see it. It's getting more detailed. It's like shrink wrapping. It's really like shrink wrapping. But you can see that each envelope here has wavy patterns inside of it. So it's kind of like growing in fractal dimension. There's like a, what do they call it? Fractal dimensionality. This is a way of calculating the complexity of a fractal surface. It's a ratio to describe how complex it is. Let's see. Oh, look. Mandelbrot kind of came up with it, I guess. But he was talking about coastlines. Let's see. So I don't know what the actual dimensioning, the dimensionality of a fractal is. How you calculate this, I'm not going to get into it. But basically, it feels as though as we jack up the number of iterations, the density of it increases. But I think that it's calculated relative from the previous to the next iteration of the fractal. Let's go back to localhost here. Whee! So as it goes up, the complexity increases, and it does so iteratively for infinity. So even if I turn it down and zoom it in on this spot here, let's see, I'll just keep clicking here. So once we zoom in here, at a certain number of iterations, this will look kind of simple again, just like the overall fractal did when we zoomed out. So to see more detail, as we get closer, we have to keep pumping up the iterations. And then it looks like this. So as you keep increasing the number of iterations, the self-similarity keeps increasing. I think that's about all I have to say about the fractal. Fun stuff, though. So you can see all the red is buried in here, and if I zoom out here, you can hardly see any of the red because it's tucked in really tight. But if I drop the dimensionality, you'll see the red easier. It'll have to drop down a few times, though. You can kind of see it's orange, not really that red, but there you have it. That's a Mandelbrot fractal set rendered in JavaScript. Totally within the realm of possibility. Pretty basic stuff. I mean, it's rendering a fractal is so much simpler than I thought. I wonder if I can pull off a Julia fractal. I wonder what the equation for Julia fractal. Is there a way to do that? Oh, I see. This is taking the Mandelbrot set, and except you're holding C constant for the entire image, and you're starting Z0 at a complex number. So let's turn this into one right now. So we'll say const Julia set equals 2. I don't know, maybe it shouldn't be 2. Let's try 0.2. Let's keep it a small number. Let's actually use math.complex here. And we'll say 0.2, comma 0.1. Just why not? Let's try that. So what we'll do now is we'll say this is z0 here. We're going to say that, I'm going to comment that out here, and we're going to say that z equals z0, or math.copy. Is there a copy? I don't know about that, but we'll try it. So we're going to try that, and we're going to replace C with Julia set. And if I'm right, that's really all that's needed to render a Julia set. Let's refresh this. Well, look at this. We've got something. Let's turn up the complexity a little bit. See what we got here. All right. So this is a little basic. Let's just snap that there, and let's change our constant. Let us change it to like 0.5 minus 0.2 or something. We'll do that. Well, would you look at that? So basically this thing's a four-dimensional object if you really think about it, because if I just change this by 0.01 here, you're going to get something rather similar to it. Let's jack up the initial iterations to 24 so we get a little more detail out of it. So you see there, we got this island here, and as I just change it, I'm just going to change this to by 0.03 here. It's still really similar. Now let's change this to like 0.3, 0.5. The islands look like they're getting a little farther apart. 0.7. So we are basically moving through slices of a four-dimensional object, where this complex number for the Julia set is like x, y, and then we got z0 here, which is z and z prime or something. I don't know what you want to call it, but we are moving through a four-dimensional object. That is rather spiffy. Oh gosh, do I have that program? Do I remember where that is? Do I even remember what it was called? Alright. Let's see if I can find it. Licensed software folder. It was called Xenodream. Do I have Xenodream installed? Nope. So Xenodream is a multidimensional fractal generator. Oh, the thing I'm actually thinking about is, do I need to worry about this? I'll just choose storage. It's an old program I got that calculates fractals. Finish. And where? There it is. I'm going to put in my key privately. I don't know what Xenodream's up to these days. This thing, I don't know if this, I don't remember how this works. It's a kind of a fractal generator. It does three-dimensional fractals. You can create meshes out of them. Let's check out the starter shapes here. Kaleidoscope. Let's see, anything cool here? Fern leaf. Here you go. So this is generated by a few holons, what they call holons, which are elements that repeat a pattern with each other, and then they copy and iterate out. And I have no idea how these work, but this is kind of a programmatic fractal generator. And then let's see if there's a way to see. As I just move this around, it just totally goes zonkers. Now it looks like evil spiky things. I don't know. I'm just destroying this slowly. But yeah, that's what it is. That's what it does. It does freaky fractal things. And then, if you want to see another cool program, you got Mandelbrot, I think. This is a 3D fractal generator, so you can see like Mandelbrot sets in 3D and stuff like that. Oh man, though, let's look at the wonder if there's any good galleries here. Gallery, yes. Let's look at the 3D. I did not have permission to look at the full thing. Okay. This is basically Mandelbrot or Julia style. Here, this is if you do z squared to the 5th plus c. Okay, okay. You know what? Let's go back to localhost and see what happens if I up the multiplier. It was the wrong localhost. I think it's actually at 1, 2, 3, 4. Here we go. So here we're back at Julia here. I'm going to go do this z to the 4th. Excuse me. Don't want to cough on that too hard there. I put a comma here. I'm going to put a math.multiply. Easy z to the 4th. Whoa. You can change the equate. Wait, what if I don't know if I could do a logarithm of z. That'd be tough. I don't know how to do a logarithm of a complex number. That's asking for trouble there. Can I do like e to the z? What happens if I raise e to a complex power? No, I don't know what to do. I am not going there. I'm just staying out of that one. Instead, let's just enjoy the complexity of a nice fractal spiral thingy. Well, my next improvements to this program was I was thinking I might just make a thing where it starts rendering in the center and spirals outwards instead of rendering top down. Just means more algebra for my brain. What happens if I set the constants of this to 0, 0? You know, the Julia constants. What if it's 0, 0? What happens then? The fractal is a giant 0. Well, how about that? If I set it to 0.5, 0.5, well, one of them's minus. That's pretty cool. What happens if I switch that to a plus 0.5 on the real? It's completely different. So it's not symmetric in that dimension. What if I set this to a minus? Okay, wait a second. On the imaginary axis, This thing is kind of looking like it's mirrored. Interesting. What if I set that to minus and I set this to plus then? Okay. So on the imaginary axis, this thing is self-similar in a mirrored sense. But on the real axis, the real axis really matters to the shape. Let's set that to 1. Oh, that's better. And there's also a really square symmetry, or at least a 1 or 2 point rotational symmetry to this fractal too. You look at the Julia here, you see that there's this kind of pattern to it. Let's try the 0.8 here. You'll see it again. It might be stretched or something, but yeah, it looks like it's got a 4-way symmetry. And this is because maybe it's because I'm raising this to the power of 4. Let's try math.multiply. What happens if I add another power to it? Z comma all these other z's here. Oh gosh, this is like a giant z chain and it's really hurting my brain. Whoa! Look, I raised it to the power of 5 and it became 5-way symmetrical. What is this thing? Let's see. I'm just gonna to the power of 3. And there you go, it's 3-sided now. What happens if I just don't multiply at all and I just... What happens? Does it become 1-sided? Well, that's kind of interesting looking. What? So that's what a z to the power of 1 looks like. It just kind of looks like this thing. It's like a circle thing. I don't know what I'm looking at. Let's try. We could try changing our window bounds to be height 8, width 16, minus 4, minus 8. No, it's just a circle. Okay, so boop 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 boop. Ah, so you have seen some things today. You have definitely seen some things. Complex numbers do funny things when you put them through iterative functions that square them and raise them to different powers, and you know. What if I multiply it by a constant? Well, that's unimpressive. That is most certainly unimpressive. Let's change. We got that. Okay, so let's make that number kind of smaller, smallish. 0.2. What? How about 6? Whoops, not duplicate. Well, I have certainly opened up a can of worms here. I'm just gonna do Z here and call it a day. Back to the... So it's impossible to get a Julia set that is one-dimensional? Because the second that I stop squaring this, is there a power? Whoa. There's a power function here. What if I do 1.5? What happens? Whoa, it feels like the Julia set is being chopped off. Dude, that's crazy. What about like 1.2? So like... Whoa, no way. It just becomes like geometrical. Okay. About 2.5 then. It's going to feel like it's chopped off again. Yeah, see? It's like you're literally slicing it. So basically, you do get rotational symmetries based on the power that z is raised to. How cool! What if we take... Oh wait, Julia set is not a value that changes, so never mind. I recant what I was about to say. I was going to say, what if we start raising this to different powers, but we'll just get different complex numbers since the value is not really changing. Log. We can do a log on this thing. Okay, we can try it. We might get undefined or something. Whoa. Talk about weird. 1.5. Oh, let's try that. See what that does. This stuff is weird. That log base 3. I think we're just kind of getting similar versions of the same thing, though. But it's really kind of cool, you know? Let's zoom in on this guy a little bit. This kind of feels like some soft painting. I really like the effect here. Let's kind of keep zoom clicking this guy here so that we get a bit more detail. I don't know. It's spiraling inwards for eternity. So we got the context menu popping up there over the top. But yeah, how about that? It's basically these chunks that get smaller in a spiral. And I guess this constant that I use as the log factor, I guess if I used E, the 2.711, then that would be the golden ratio spiral, kind of. So, we learned a thing about math.pow 2.71 to the z. Can I do it? What even am I looking at? Let's try zooming in on this fringe here. Because there's a lot of colors packed into that little fringe. It's not quite in the center of the screen, so you can see that y is capped at -2 right now. So I have to keep recalculating where the center is as I zoom in. But once I get to the center of the screen, I could zoom in a few more times. See, now y is away from the edge of the screen. The edge of the frame, you know, the -2 +2 limits I was telling you about. So this is not as interesting as I had hoped for. How about math.multiply z here? What happens if I do that? If I just multiply z times z and raise 2.71 to the power of that? Well, what am I even looking at? Something like Pink Cotton Candy Land or something? I have no idea what this stuff is. Let's go dive into it. Let's dive into the kingdom of Cotton Candy Land. It's like a planet that has lots of hills, except the hills connect to other planets or something strange. Did I zoom into absolutely nothing? Am I lost? I think I am. I'll have to bail. Well, anyway, I think you've seen enough for today. Goodbye.